All right, this is going to be our lecture on analyzing multiple populations of data. Today, we're going to be looking at a couple of goals. The first is to figure out how to conduct hypothesis tests when we're dealing with two populations. We're going to talk about constructing confidence intervals with two populations, and we're going to talk about how to adapt our existing confidence intervals and hypothesis test settings for a situation when the population standard deviation is unknown. We're going to have no new vocabulary here, but we are going to learn how to use the data analysis tool pack in Excel. We're going to use the t.inv function um, in Excel, and we're going to use the stdev.s function. Both of these are going to be useful when we're considering how to modify hypothesis tests and confidence intervals for situations when the population standard deviations are unknown. So let's turn to that example first. Like I said, we're going to jump right into what happens if sigma is unknown in a simple situation. We're going to look at a two population hypothesis test confidence interval question. We're going to recognize that we're looking for the same statistical objects every time and do a little bit of work in Excel. All right, well, what we've done basically since we've started working with the central limit theorem is we've figured out that we can use samples of data and the central limit theorem to help us determine plausible values for unknown parameters like the population mean, mu. And so we've conducted hypothesis tests regarding the true value of mu. We've also constructed confidence intervals for plausible ranges of mu given samples of data we've observed. Yet in both of these situations, we've presumed that we know the population standard deviation sigma. Now, this is a bit of a weird situation because if it's if it's if it's feasible to know a population characteristic like the standard deviation sigma, then it's weird that we would be estimating the population mean mu. Another way of saying that is if we don't know anything enough about the population to know the mean, why should we presume that we know the population standard deviation? Well, the rationale behind why we've done this is because the central limit theorem tells us that the sampling distribution for our sample average is going to depend on this parameter, the population standard deviation sigma. But the good news is we're going to be able to modify our approach for a more general version of hypothesis test and confidence intervals when we no longer presume that sigma is known. So very simply, what are we going to do if sigma is unknown? Well, we're going to have to make just two modifications to our existing approach. The first thing we're going to have to adjust is our critical value. The last thing is our standard error. And we're going to remember here that anytime we've been dealing with hypothesis test or confidence intervals, we've only really needed to know three things: point estimate, critical value, and standard error. And the adjustments we're going to have to make are going to come in terms of our standard error and our critical values here. Okay, first and very simply, as we've dealt with before, when we don't have a population value, it is standard to substitute it with its sample standard deviation. Now, what we're going to do here is exactly that. Anywhere we would use the population standard deviation sigma in our calculations, we're just going to replace it with the sample standard deviation. We're going to call that guy sigma hat. Now, inside Excel, we would use the function stdev.s of our data range. And this would be wherever your data is that you've sampled from your population. Now, there are two functions in Excel which begin with stdev. One is .p, and that p stands for population. And the .s stands for sample. Now, for reasons that we are not going to get into in this unit, the sample standard deviation has an adjustment to it that makes sure that we don't have a bias lurking around in this, this estimator. And so it's important that you use the stdev.s option when you're calculating your standard deviations. Second, we're going to have to modify how we calculate our critical values, particularly because when we are using the sample standard deviation sigma hat, this too is subject to sampling error in the same way that our sample average x bar will not ever be exactly equal to the true population mean, neither will sigma hat be equal to the population standard deviation sigma. And so we're going to use a different distribution to get our critical values here that accounts for this additional estimation error and uncertainty. And that distribution here is going to be called the student t distribution, or generally we'll probably just call this the t distribution. As before, when we were looking at our critical values in the context of the standard normal distribution, we would use the norm.inverse function. Here too, we're going to use an inverse function, but this will be the t.inverse function. And unlike the norm.inverse function, which required a mean, standard deviation, and a data point, the t.inverse function is going to require this percentile information. What we're going to do instead is use the student t distribution. Now, the student t distribution is the what we're going to do instead is use the t distribution. And as before, we're going to use an inverse function the same way we use norm.inverse to calculate our critical values when we assumed sigma was a known population parameter. Here, we're going to use the t.inverse function. And we'll use this t distribution every single time we don't know what the true population standard deviation sigma is. That'll be true both when we're using a 1 population and a 2 population test. The t.inverse function is going to use an argument here that's going to take in the percentile, the area to the left of a point. That's the same as the norm.inverse. But the only other requirement for this function is an argument we're going to call the degrees of freedom. I'll write this in shorthand with df. And the degrees of freedom is, well, let's just talk about it a little bit more in detail right now. The degrees of freedom is loosely a way of accounting for the increasing reliability of your estimate of the population standard deviation as your sample size increases. So the more degrees of freedom you have, the more data you are using to account for the potential for sampling error, the more that sampling error is mitigated, the more reliable our estimate of the sample standard deviation becomes. Okay, and so this t distribution is going to be a function of this argument called the degrees of freedom. Now, just like the standard normal distribution, the t distribution is also centered on 0. It's symmetric around the mean. The mean is equal to the median. All these properties look the same. However, the standard deviation here is larger and a function of the degrees of freedom, so that as the degrees of freedom get larger, the t distribution limits to, it gets closer and closer and closer to the true population standard deviation. Because it is a wider distribution, that means our critical values at any percentile in the data will be larger in absolute value, which means we're more likely to fail to reject null hypotheses, and our confidence intervals are going to be wider. Now, that's not a problem for us. We want them to be wider because, again, there's additional uncertainty as we're not only estimating the population mean in order to calculate a confidence interval here, but we're relying on another estimate, the population standard deviation. And so these confidence intervals are going to need to be wider to account for this uncertainty, and the t distribution is precisely how we do this. All right, so we're going to take an example here of going to calculate a confidence interval for a single population parameter, and we're going to need this tool here where we're going to find out that the degrees of freedom is the number of data points we use to calculate our sample average minus 1 when we're looking at a single population. So let's do an example here. Suppose we had a sample of 10 observations from an unknown population. Now, I'm not telling you anything about this other than we have some data. I'd like you to calculate a confidence interval for the true mean of this population. Okay, so this is a random sample of 10 observations from the population. We want to construct a 90% confidence interval. Now, we always need to do the same 3 things. We're going to need to calculate a point estimate, critical values, and standard error. Now, as we said before, the point estimate is not going to change at all. This is just the sample average of the data. And so we know in Excel, I could take the average of A to A, and that's going to go ahead and calculate for me the sample average. It's going to add up all of these objects and divide it by 10. And we're going to get 19.2 as our point estimate X bar. Our critical value here, we're doing a 90% confidence interval, which means this is still a one, we would write this as a 1 minus alpha confidence interval. So if we're looking at a 90% confidence interval, that means alpha has to be 10%. And just like before, where we would come up with the 5th percentile and the 95th percentile of the z distribution, if we were going to come up with a 90% confidence interval, here too, we're going to come up with a 5th percentile and 95th percentile, but of the t distribution, okay? And so again, here in Excel, we can see that the function is equals t dot inv, t dot inverse, of the area to the left of the point. We're looking at the 95th percentile, and the degrees of freedom is that argument that I told you about. Okay, this is the thing that tells us how reliable our estimate is going to be. And so the larger this is, the closer these t statistics, as we'll call them, are going to get to the corresponding z-scores. Now, again, the degrees of freedom here is the number of data points we are using to calculate our sample average, which is 10 minus 1. So it would be 9 degrees of freedom. So our critical value then is just this 1.83. So we've got our two pieces, point estimate, critical value, and the standard error is the other place we have to adjust our calculation. Now, what we've said when we're calculating, when we're relying on some information about the standard deviation is we can no longer use the population standard deviation sigma, but the sample standard deviation. So what we're going to do is we're going to calculate that using the stdev.s function of this data range A to A here. And it's going to calculate for us the sample standard deviation of that data. That works out to be 9.908, okay, which I've rounded to 9.91 here. And as before, we're going to divide this by the square root of the sample size, okay, which means that our standard error is 3.13. Now, we're going to do the exact same things we've done every other time when we're calculating a confidence interval. We're going to take our point estimate plus and minus our critical value times our standard error. So we would say that the 90% confidence interval for the mean of this population is 19.2 plus or minus 1.83 times 3.13, okay? Or I'm 90% confident that the mean falls somewhere in this range of values. Now, what we're going to do is we're going to extend our analysis here, or our set of questions we can answer from one population to two. Now, we're going to start with a very simple reason why we might analyze two populations, or what we think are potentially two populations, and that would be an attempt to answer a causal question. Now, what I mean by causal is we might think that there is something that we could do to impact some outcome in the world. Okay, so for example, one might want to know, do changing tax rates impact unemployment? And so we would want to have some comparison of unemployment rates for people who had the old tax rate and people who have the new tax rate. What we're thinking about here is really kind of setting up an experiment. Now, experiments in business and social sciences more generally run into a series of additional problems that treatment is not usually randomly assigned to groups. And as we get later in this course, and as you take more analytics courses, you'll learn tools to deal with that. So what we're going to do now, start with a really simple thought experiment, which is that we could randomly assign people to two different groups to quantify some sort of causal effect of some intervention on an outcome. So let's look at a really simple one. Let's ask whether masks reduce the spread of COVID-19. So before we get into this, yes, they do. But if we were analyzing it for the first time, what would we do? Well, if we were doing this in a scientific way and avoiding all sorts of questions about the ethics of such an experiment, what we would do is we would randomly select two groups of people. We would give one group masks, we would give the other group no masks, and we would see if the number of COVID-19 infections looked different among these two groups. Okay, so let's suppose we're just going to count the number of new infections we observe within these two groups separately over the course of 10 days each. So we're going to have 10 samples that say how many people get impacted in one group, how many in the other. Well, then what we could do is we could compare the sample averages, the average number of daily infections in a population that had masks, the average number of daily infections in a population that had no masks, and we would make a comparison of these two. Okay, the idea behind this is, of course, that is each of these sample averages is representative of a population mean, then comparisons of sample averages are a way of approximating a comparison of two unknown population means. So suppose that we were to find that in our 10 days, the average number of new cases, if people were wearing masks, was 1.8 cases per day. And among the no mask population was 3.5 cases per day. The question we would want to really ask ourselves here is if we could actually say that these numbers are statistically different from each other. Now, what I mean by this is we need to account for the fact that sampling error is going to mean that sometimes we are going to end up with numbers that are different from their true population values. And even though our sample averages here are unbiased and consistent estimators of the population means, since there will be sampling error, the comparison of these two sample averages could, in theory, understate or overstate the effectiveness of masks. And so what we're going to do is we're going to look at two possible cases here. One is there is absolutely no difference between the number of new cases on average between the population that wears masks and those that don't. And the other is that there is some kind of difference. Okay. So what I want you to have in mind is this first diagram. Okay. So in our first possible scenario, what we're going to say is that the population mean for the group that wears no masks is the same. Oops, this should say masks. The sampling distribution here for masks is equal to the sampling distribution for no masks. And what that means is that in truth, we have taken two sets of data from the same population. It happens to be the case that the set of people that we selected who did not wear masks happened to have a lower than average number of cases. It also may coincidentally be the case that the set of people who did not wear masks had a higher than average number of cases just by sheer sampling error. Okay, if these two come from the same distribution, the central limit theorem tells me that in expectation, they should both be the same value. That is the middle of this gray distribution. So one possibility is these two sets of individuals or two sets of people are actually likely to get COVID at the exact same rate. The only difference here is random chance in the sample we got. If we had done this again, we might be just as likely to see them in the opposite direction, or maybe both of them right in the middle, okay? The alternative possibility, okay, is that the population means, okay, here in blue, we're going to have the population that wear masks, and red is the population that wear no masks. We would say that the population means are actually truly from different populations. That is, the exposure rate is different. Therefore, the likelihood of getting COVID is different in each of these two populations. Okay. In this case, the fact that these are two distinct values is representative of the fact that they are from different distributions themselves. The mean exposure for people who do not wear masks is different from the mean exposure for people in populations where everyone is wearing a mask. Okay, these are two different possibilities and encompass a null and an alternate hypothesis. That is, in one situation, we're saying both groups come from the same population or they have the same average. The other one, we're saying they do not. Okay. Now, this sounds like a slightly more complicated question, but it's not. These are the same things we've been doing over and over. We're going to need to do the same set of steps we would always do for a hypothesis test. The first one is to write out a null and an alternate hypothesis. And it has to be that these are both in terms of the population parameters are mutually exclusive and exhaustive. So in the first situation, we're going to say that the true average rate of infection for populations where everyone wears a mask is equal to that of the population where people do not wear a mask. Okay. Notice we're not taking a claim here on what the actual number is. We're just simply saying that the means of these distributions are equal, which means that the difference in the means is 0. If I were to take the average, the true population average among the population that wore masks and the true population average among those that did not wear masks, the difference would be 0. That's another way of saying the averages are the same. Then the alternative hypothesis, again, we don't have to pick what these numbers are. We're just going to say or they are different. Now, we're going to go through our next set of steps here. We're going to calculate a point estimate. Well, since the population object we are after is the difference between the population mean for mask wearers and the population mean for non-mask wearers, the sample average, this difference in these sample averages, okay, works out to be this point estimate. And the reason is, since this is an unbiased estimator for this, and this is an unbiased estimator for this, the difference between them is an unbiased estimator for the difference between those two populations. Now, in terms of our critical value here, what we're going to do is rely on the exact same intuition we did before, which is that if the population standard deviation is known, then our critical values are going to come from a z distribution. Alternatively, if they're unknown, they're going to come from a t distribution. The standard error here in the situation where we're dealing with two populations is actually a rather unfriendly looking formula, depending on your assumptions about these population standard deviations. And so instead of actually encouraging you to memorize them, any situation like this, I'm going to have you actually evaluate this hypothesis test in Excel, and I'm going to show you how we would actually calculate point estimate, critical value, and standard error from inside Excel. I have generated some pseudo data on a mask wearing population and a non-mask wearing population. Okay, so mask wearing population is here in A, the non-mask wearing population is here in B. And we could do some really simple stuff. I could go ahead and say, I want to know X bar and X bar. So this is going to be my two sample averages. And I could take the average of this first group. And then since I've formatted this cleverly, I can click and drag this over. Okay, and what we're going to see are these are the same population, sample averages that I mentioned on my previous slide. The mask wearing population has a sample average of 1.8 cases per day. The non-mask wearing has 3.5. Now, it will turn out that in fact we can do our whole hypothesis test much more transparently just using something called the data analysis tool pack. So inside Excel, what we're going to do here is we're going to click on the tab that says data. We're going to come over here to the part that says data analysis. And then once we've done that, there's this tool pack that will pop up here. And this is going to give us a variety of different analytical tools that we're going to continue using as we move on to correlation analysis, regression analysis, ANOVA, and the like. But what we could do right here is if you scroll all the way to the bottom, you're going to see a series of tests here. One is the t-test, and the other is a z-test. Now, there are a variety of t-tests here. The first is called a paired t-test. We're not going to address that immediately. And the last two are statements, are types of t-tests where the way we calculate the standard error is going to depend on whether we can assume that the population standard deviations for both of these groups is equal. Now, there are situations where that's a useful thing to do, but it is a restrictive assumption. You're basically making a claim about something that you really don't know much about. And so generally speaking, out of conservatism, people will treat these as if the population standard deviations are unequal, that is, or they are presumed at least to be unequal. And so anytime you see some kind of data like this, we're going to go ahead and assume that we are looking at a two-sample test with unequal variances. Then you can go ahead and hit OK. Once you've hit OK, you'll be able to go ahead and select the data. Now, these data correspond to the two populations that we had identified in our hypothesis test. In the first one, we said we're going to look at the population of mask wearers. Okay, so you'll see here in my data range, I have this highlighted A1 to A11, and then I'm going to click in variable range 2, and I'm going to say, B1 to B11. And I'm going to make sure that I've got this option that says labels checked, because that's going to make sure that when Excel spits out a table here, it's going to be labeled nice and cleanly for me. Now, right off the bat, you're going to see an argument here. This will be empty in your screen, but I've previously filled this hypothesis test out, and it says, what is the hypothesized mean difference? That is, under the null hypothesis, what is the difference between the population that wears masks and the population that does not? Well, under the null hypothesis, the hypothesized mean difference is 0, okay? Then here again, what we're going to do is we're going to evaluating this hypothesis test with a particular level of confidence, okay? Do we want a 90% confidence interval? Do we want a 95%? Do we want a 99%? Here again, we're picking alpha, which is going to be 1 minus alpha is going to give us our level of confidence. So we're going to do a 95% confidence evaluation for this hypothesis. The last thing I'm going to do here is I'm going to select the output range. I'm going to put this here right in D1 so that we can see the output right here on the same sheet. And I'm going to hit OK. Now, Excel will then spit out this table for us. And this actually has all of the information we need in order to calculate our both our confidence interval and our hypothesis test. So let me talk you through what this table says. First of all, this argument here that says mean, this is the sample average. Okay, this is the sample average, which means this is X bar. We can see that this matches our number right here. And this is X bar for no masks and matches our number right here. Okay. It will also indicate for us the hypothesized mean difference, the degrees of freedom used to calculate our test statistic. And again, here, because we are assuming that the population standard deviations are unknown, that is, we have to estimate them from the data, our confidence, or excuse me, our critical values here are going to come from the t distribution, not the z distribution. Okay. Now, this t-stat that you see here, this is in fact our test statistic. Okay, this is our point estimate minus our hypothesized value divided by the standard error. And it turns out that the test statistic here is minus 3.59. Now, as we know, when we're going to conduct a hypothesis test, we would compare that test statistic to some critical values. And Excel will also provide these for you. So Excel is going to indicate for you the two-tailed critical value. And that two-tailed critical value that it reports will always be the positive critical value for this test. Now, it's up to you to recognize that a two-tailed test actually has two critical values, two rejection regions. That is, everything to the left of minus 2.1 and everything above 2.1. And so if we were to draw out our sampling distribution here, our test statistic distribution, the rejection regions would again be everything above this critical value and everything below the negative of this critical value. And we can see immediately that our test statistic of minus 3.59 is in fact below minus 2.01, which means it's in the rejection region. So we would reject the null hypothesis. That is, we would reject the hypothesis that both of these have an equal mean. Now, what we can also do is calculate our point estimates, critical value, and standard error in order to construct a confidence interval. So we can see right off the bat that we could do a one or two-tailed test right out of this without having to do any calculations. Excel is going to spit out this information for us. On sheet 1 here, what I've done is I've indicated for you where we would get the information to get the point estimate, critical value, and standard error. And so I'm going to talk through those briefly. What we have said here is that the point estimate for the difference in the true population means of our two groups is the difference in the sample averages. And so to get this, we could simply fill in one cell that says, I want you to take the difference between what is in cell H4 in blue here and I4 in red here, and you're going to get minus 1.7. So our point estimate for the difference in true population means is minus 1.7. Now, what does this mean? This means that on average, the no mask population saw 1.7 more cases per day than the masked population, okay? So that when we took the average masked population and subtracted the no mask population, we get a minus 1.7. The critical value here, again, we said we're just going to take this right from our critical two-tail. This critical value will depend, of course, on our degrees of freedom, but also the level alpha we selected when we were evaluating our data analysis toolpack function. The last part here is the standard error. Now, the standard error is going to be given by, as always, our point estimate minus the hypothesized value under the null and divided by standard error. That's our test statistic. Okay, this was the case when we were dealing with a z-score. It was the case It's also the case when we're dealing with the t-distribution. So what we're going to do is we're just going to work together and see how this would come about. Well, we can see here that our point estimate, as we've already calculated, is minus 1.7. The value, the difference between the two true population values under the null hypothesis is 0, which means the point estimate minus 0 is the numerator of this expression. That thing divided by standard error is equal to our t-stat. So what we can say is that minus 1.7 divided by standard error is equal to minus 3.59. Okay, that's it right here. What that means is we can simply rearrange this expression. Okay, we could take the standard error, multiply both sides of this expression by standard error, and divide both sides by the t-stat in order to back out standard error from this table. Okay, and we can in fact see that that's exactly what I've done right here. I have taken the point estimate, which I previously calculated, divided it by the t-statistic, and that's going to give me my standard error here. All right, now again, what we can see here are these same objects, okay, where we can see how these have been arranged. We can calculate a 95% confidence interval as the point estimate minus the critical value times the standard error, and the point estimate plus the critical value times the standard error. So we would say that the difference in the number of new cases among a population that wears masks versus those that do not is the population that wears masks has between 2.7 and 0.7 fewer cases per day on average in this made up sample of data I have here for you. Again, and we can also use these t-stats and critical values as a way of evaluating whether we would reject or fail to reject the null hypothesis. As before, if our confidence interval breaches 0, meaning it's the lower bound is negative and the higher bound is positive, we would say that this confidence interval gives me the range of plausible values for the difference between these two means, which means that if that is possibly 0, then we would always fail to reject the null hypothesis that 0 is a plausible value for the difference in those two population means.